Okay, so here's the exam review for exam 3, okay? And I'm going to go through all 20 questions as the class average on this is not ideal at all. And there are some questions that's causing confusion. I've been answering emails about them. And now, so let's go. First question, this one isn't having much of a problem. Which of the following molecules central atom has expanded octet? So expanded octet is where your central atom has more than 4 pairs of 8 electrons around it. Okay, so all you really need to do is just join the Lewis structure of the molecules. So carbon dioxide, chlorate ion, PF3, ClF3, and for ClF3, because it's 7 plus 7 times 3, 28 electrons, 14 pairs. So after you took care of the 3 fluorine atoms, non-central atoms, with 12 pairs of electron, you ended up having 2 pairs left. And both of those 2 pairs have to go on to the chlorine as the central atom. And silicon tetrafluoride, pretty easy stuff. Total of 32 electrons, 16 pairs. So once you draw the correct Lewis structure, I think it's pretty easy to see. Your chlorine here has 5 pairs of electrons surrounding it, and therefore it has an expanded octet. All right, the next question is one of those that has a little bit of argument. I think I received probably 3, 4 emails regarding, well, 2 of the answers. Okay, now, there's not a whole lot of argument on A, D, and E here. Okay, if you draw the Lewis structure, now this is 6 plus 7 times 2, so a total of 20 electrons, 10 pairs. So oxygen, fluorine, 8 pairs, 2 more on the central atom. Okay, the xenon difluoride, I think we've done this before, 8 plus 14, so 22 electrons, 11 pairs. So we did this, I believe, in one of our recitations. You have 3 pairs left, and that goes on the central atom. So silicon silate ion, SiO. This one actually have the exact same electron counts with the SiF4 that we did earlier, so it's the exact same structure. 32 electrons, everybody has octet, and it's all good. Now, people's argument, it's mainly focusing on the O3 molecule and the CO2 molecule. And I think everybody recognized that, okay, with a total of 9 pairs of electrons, okay, 6 times 3, so 18 valence electrons, 9 pairs. Now, most people can see that, okay, that's my 9 pairs of electron, and central oxygen doesn't have an octet, and that means one of these 2 oxygens and should be taking one for the team, and the result is that either this guy is forming a double bond, or the other guy is forming a double bond. And to be fair, okay, they would have to, because they're in equivalent situation, the two non-central oxygens are in equivalent situation, so they have to take turns in contributing to that double bond, and that's exactly what we discussed we defined in our class for resonance. Okay, resonance is defined as non-central atoms taking turns to make multiple bonds to satisfy the central atom's octet. Okay, equivalent non-central atoms. Now, and what people email to argue with me about is mainly on, okay, carbon dioxide could, as we discussed this molecule before and in our class, and when we draw Lewis structure, this was the Lewis structure that we draw, okay, to use 8 pairs of electrons to create octet for everybody. But some people did this, and yes, this does satisfy the octets of both oxygen, okay? Now, and you also with 8 pairs of electrons. And people are telling me that they believe this is resonance structure, okay? And also I've been emailed with, links on internet that's saying that this is resonance. Okay, so let's put it this way. A lot of the contents in Chem 115, okay, because this is an entry-level class, okay, and we're touching so many different aspects of chemistry, okay, a lot of the contents in Chem 115 are simplified from the actual situation, okay. We are making general rules that's not accurately describing, okay, what the scientific society, the chemical society is viewing on certain topics, okay? But we actually took a very simple approach because this is, after all, an entry-level course. And this means a lot of the topics that discussed in Chem 115, if you really go on internet and search for it, okay, you would find different opinions about it, okay? We may taught it a certain way. Now, in Chem 115, we may tell you, okay, a certain generalized results or rules in Chem 115, but you would see different results if you look into more details of it, okay? And there are even things that even today, scientific chemistry society holding different opinions on, and you may be only introduced to one opinion in this class, okay? But one thing couple things for this question determines that I'm not going to count it as the correct answer. Number one is that when you say, well, it has 3 equivalent resonance structure, okay, one thing I believe that we emphasize in our class, is that resonance structures are equivalent to each other, right? These two, yes, they are equivalent to each other, okay? But these two and this one, they're not equivalent to each other. Okay, matter of fact, now, if you calculate formal charge on each of the 3 atoms, okay, and for this one, this structure, you're going to get 0, 0, 0, okay. Now, for oxygen is 6 minus 1/2 times 4, minus 4, and then for carbon, it's 4 minus 1/2 times 8, okay. For these 2 equivalent structures, for the single bonded oxygen, you would have 6 minus, so 6 original valence electron minus 1/2 of 2 bonding electrons, so 6 minus 1 minus 6 non-bonding electrons, so this would be -1. Carbon would still be 0, and this oxygen would be actually 6 minus 1/2 of 6 bonding electrons, so 6 minus 3 minus 2, which is +1. And of course, the opposite here on the other one, this would be +1, 0, and -1, okay? And 2 general rules that we talked about in formal charge is that, now, with different Lewis structures that could be drawn for the same molecule. Okay, now when you apply formal charges, we want the formal charge to be as close to zero as possible. These two are not equivalent to each other, and this is obviously the preferred structure of the three, because you have all three atoms having a formal charge of zero. Okay? And when you don't have equivalent and all three structures being equivalent, and also when you have one of them being clearly the preferred structure, at least in the definition we discussed in our class, and I have to based on all my questions in the way that I teach you in this class, okay? Because otherwise it's not fair to you. No? And based on all that, I would say, at least for the material that we taught in this class, this is not resonance. Because this one is a clear match of the definition that we discussed. Okay, and this one is, CO2 is not. All right, so next question, paramagnetic and diamagnetic. Okay, paramagnetic means you have unpaired electron. Okay, so you look at zinc. Zinc is argon, 4s2, (3d10). Every single orbital zinc have here is completely filled. Okay, so definitely diamagnetic. Yeah. Selenium 2 negative ion. Okay, yeah. Oh, okay, and in our question, I believe we don't have that positive charge on copper. No. And selenium 2 negative ion actually have the krypton electron configuration. Noble gas electron configuration, definitely diamagnetic. Magnesium, okay? Magnesium is number 12, neon 3s2. S orbital have 2 electrons paired up. Neon is noble gas, so this is definitely diamagnetic. Okay, yeah. And copper, okay, hold on. The question that you see on the paramagnetic, the question that you see on the exam, let me, it does have copper plus. Okay, now, so copper plus ion, okay, copper atom now is one of the exceptions that we discussed before. This is argon 4s1 3d10. Okay, now copper plus ion 1 plus means, and we talked about this in our lecture, that when you're making positive ions, okay, you're losing electron from valence shell. Now, what is valence shell? Valence shell is the highest number shell. Okay, now in this situation for copper, that is clearly 4s1. So Cu plus would be losing that 1 electron, and you ended up with argon 3d10. Now, argon is completely full, and 3d10 means full 3d orbital. So that is diamagnetic as well, okay? And that leaves you with the only other possibility. And now let's see titanium. Titanium is argon 4s2 3d2, okay? Now, 2 plus means losing 2 electrons, and we just said losing electron from valence shell. Well, between 4s and 3d, which one is the valence shell? 4s is, if you agree that 4s is your valence shell, and then you're going to have to lose those 2 electrons before you touch 3d. Okay? And if you do that, then titanium 2 plus ion would have argon 3d2, and 3d have 5 orbitals, and 3d2 means you have 2 electrons there. They have to be singly occupied with the same spin, according to Aufbau principle. And now you have unpaired electron, and that is paramagnetic. Okay? Now, the question after that didn't have too much argument. Now, CO3 is one of those ions that we say have resonance structure because with the electron count, one of the 3 oxygens need to make a double bond to satisfy carbon's octet. So that or that. Okay, so 3 resonance structures. And now, this, looking at any one of these, that means you have 3 electron clouds surrounding the central atom, and 3 electron clouds gave you trigonal planar geometry, and because you have no lone pairs, it's trigonal planar shape as well. This is what trigonal planar look like. Well, what's the bond angle? Clearly 120 degree. So C right there is your correct answer. Okay. Correct electron configuration for nickel plus 1 ion. Okay, well, what's nickel ion's electron configuration? Nickel is argon 3d 4s, sorry, 4s2 3d 8, 28 electrons. Okay, now plus 1 charge means again losing 1 electron from the valence shell. Okay, argon 4s1 3d8. Isoelectronic question, and the question you see on the exam is a Cu plus 1 ion, and also I believe that the 5 choices are nickel plus, zinc ion, and this one here, it changed on the real exam to nickel. Okay, so we already discussed copper ion, okay, copper plus 1 ion. And based on our rule, losing one electron from the valence shell, okay, for D10, 3D10, sorry. Okay, now, zinc is argon 4s2 3d10, and the electron count is not even correct. Okay, nickel plus is, we just discussed that, argon 4s1 3d8. Okay, now cobalt doesn't even have the correct electron count, argon 4s2 3d7. Zinc 2 plus though. Zinc is that. Zinc 2 plus means losing those two 4s electrons. Argon 3d10. That is your correct answer. And of course, no, there are emails sent to me regarding nickel and saying, well, nickel have the same electron count. And that is correct. Nickel does have 28 electrons, just like copper 1 plus ion. After all, copper is number 29. Okay, losing one electron means you have 28 electrons left, and nickel has 28 electrons. But those 28 electrons for nickel, it's argon 4s2 3d8. Yeah. They have the same number of electrons, but they don't have the same electron configuration. Isoelectronic, as we stated in our class, same electron configuration. They're clearly not the same electron configuration, and therefore nickel is not isoelectronic with copper plus ion. Okay, now the calculation on this exam are all pretty simple. Okay, now the only thing that could cause mistake here is this is actually one of the least mistaken problem. That wavelengths equal to h over mv. Now, 6.626 times 10 to the negative 34s. Now, the only thing that you need to take care of is that mass here in de Broglie wavelengths calculation is international standard unit, and this need to be in kilograms. And you have grams here, so you got to make it into kilograms. Now, you did that conversion, then you're going to get the right answer, because everything else is just plug and chug. Okay, and with that, now you would calculate C being the right answer. And without that, if you use 38, then you're going to end up with that, and that's, of course, wrong. No. All right, so quantum number sets, the next one. And this one is not, doesn't have too much arguments on it. No. So tungsten. Okay, tungsten is on the periodic table in number 74. Okay, number 74 is in the 6th row in the D area. That's your S, P, and D area. And tungsten is in the 6th row here. Okay, and in the 6th row, that means you start with 6s. Okay, after 6s, the next orbital is 5d. Okay, the highest energy orbital for tungsten is 5d. And once you determine that, now 5d tells you n equal to 5 for sure. That's your shell number. Okay, 5d also means that your L has to equal to 2. 0, 1, 2, 3, SPDF. Okay, so that one's gone, and this one's 5 and 2, and then the rest of them just need to stay with the rule. ML, okay, is negative L to positive L. And negative 2 is fine with L equal to 2. MS need to be plus 1/2 or negative 1/2. You have plus 1/2, so you're good. Now, and the other two answers, if you look at it, that's 6, that's not going to work. That's 3, that's not going to work. So that was our correct answer. Now, polar, non-polar molecule is all about shape. Okay, so let's get Lewis structure. This is NHHH tetrahedral. No lone pairs, so tetrahedral shape. Yeah. And tetrahedral shape with all equivalent bonds. This is a very, very symmetrical structure. This is absolutely nonpolar. Okay, SO3. Now, SO3 is actually just like CO3 2 negative. Yeah. And you would have lone pairs, and you would find you run out of your 12 pairs of electron, and one of your oxygen need to take one for the team, make a double bond to give your sulfur a octet. And then of course you look at this, you know this is resonance structure and whatever, okay, but you ended up with 3 electron clouds surrounding your central atom. This is trigonal planar. And again, trigonal planar is a symmetrical structure, and we know in resonance, okay, the result is all 3 bonds are equivalent to each other. Okay, and symmetrical structure with equivalent bonds and same non-central atoms. This is definitely nonpolar. Xenon tetrafluoride, if you calculate and draw the Lewis structure, and you would have a total of 18 pairs of electrons, okay? 28 from fluorine and 8 from xenon, so a total of 36 valence electrons, 18 pairs. And this is used 16 and 2 more on the central atom. And that Lewis structure tells you that you have 6 electron clouds, so octahedral geometry, but with 2 lone pairs. And if you remember our summary of VSEPR, you know that this is square planar shape. Well, square planar look like this. And with all equivalent bonds, okay, each of the 2 opposite bond dipoles cancel each other, so this is nonpolar as well. CS2 is just like CO2, because oxygen and sulfur is in the same group, so if you draw the Lewis structure, it should look like that. And 2 electron clouds surrounding the central atom, and that means you have linear shape and no lone pairs, linear shape of molecule, and 180 degrees against each other with the same bond. No argument. Bond dipoles cancel. This is nonpolar as well. And that leaves you with the only choice possible, and CR3. And if you draw the Lewis structure, you're going to see that this guy has 3 fluorines and 2 lone pairs. Okay, and that's 5 electron clouds, trigonal bipyramidal geometry, and with 2 lone pairs, this is T-shape. Well, with T-shape, the 2 on the side cancel each other, nothing's cancel the bottom one, and that bond dipole, if it cannot be canceled, then you would have a polar molecule. Okay, now, maximum number of electrons that can be filled into ACE shell. Now, as I put these the exam that I typed up on computer onto the eCampus for our real exam, I made changes to them, and this is A's shell. And the calculation of the maximum number of electron in a shell is 2 and 2, so 2 times 64, 128. Not much to say there. No. Well, this is another calculation problem which majority of people have no problem with. No. Energy should equal to hc over lambda. Okay. No. And then multiply by 1 mole Avogadro's number, 6.022 times 10 to the 23rd. Okay, so plug your numbers, make sure you know this is times 10 to the negative 9th meter, and you could get the result. Now, next question, when it makes onto the exam, there are some changes. And I wasn't asking the designation of the orbital with the highest energy. I was asking that the highest, the valence shell number. Let me look at the question online and get the exact wording that I have. The valence shell number is, and the 5 answer choices are actually 4, 5, 6, 7, 8. Okay, so if you look at element PA, this is number 91, okay? And number 91 is in the F area, okay? So its highest energy orbital is the F orbital, okay? But highest energy, as we discussed earlier, and also as we discussed in class, highest energy is not your valence shell. Your valence shell is the highest number. So what is the shell with the highest number? If you place PA into the periodic table, although it's in the F area, okay, but if you follow the numbers, okay, number 91 is right after in your periodic table. Okay. In row number 7, it starts with number 87, 88, 89, okay, and then of course 90, 91, okay, yeah. And 91 should be in 7th row. Elements in the 7th row means what? That means your element electron configuration ended with, okay, some electrons on 7s, and then possibly 6d, okay, and possibly 5f. Highest number, you definitely have electron in 7s. 7 is your highest number shell, and that shell number, no, that's your valence shell. That shell number is 7. Okay, no. The hydrogen spectrum problem is one of the least mistaken, very easy and straightforward calculation. Just stick your number into the Rydberg equation that was available on the exam, so I'm not going to spend too much time on this. No. Correct answer is 7. Okay, no. Rydberg equation 1 over 2 square minus 1 over n square equal to 1 over 397 nanometers. Stick your Rydberg equation in, you're going to find your n equal to 7. Okay, so now, all right, the next question, which of the following elements' third ionization energy is this highest? Okay, and I believe in our recitation we discussed this in detail. And I told you guys on the recitation there will be some question like this on the exam. And highest ionization energy. How does highest ionization energy happen? Highest ionization happens when you break octet. Okay? Now, because this is where your atom or ion is going to fight you the most. I go through all these problems to get an octet, and this is perfect, I love it, and you want to take the electron away and destroy it for me. Well, I'm going to resist. Okay? And if you're going to pay me with energy, you better pay me a lot. Now, so which element, okay, will break octet when it loses 3 electrons? Okay, aluminum has argon. No, not argon. Neon. Sorry. 3s2, 3p1. Okay. Now, if anything, its third ionization energy would actually be very low, because you lose 1, lose 2, and when you lose, after you lose that third electron, you're going to get an octet. So you're not breaking octet with the third ionization, and your aluminum is going to be happy in whatever energy you pay for him, because you're making him look perfect. Okay, barium though, this is where you have Xeon and then 6s2. Okay, yeah. First electron, fine, take it. I want to get +2 charge because barium is in group 2A. Okay, second one, okay, yeah. Take it, I'm happy. But once you take away those 2 electrons, you get a perfect Xeon octet electron configuration. Yeah. Now if you're going to take another one, barium is going to fight you, okay, because he can't afford to lose one, okay, to break octet. So that is your obvious choice. Now, potassium is in group 1A, so this end up with 4s1, you lose 1, and the second one is going to fight you. Okay, by the time you got to the third one, it's not going to fight you as much. You already don't have an octet. He already doesn't have an octet anymore. Now, selenium is 4p4. Losing 1, losing 2 doesn't make them. Losing 3 doesn't make that much difference. Iodide is 5p5. It wants to get electrons. So losing 1, losing 2, losing 3. Barium is the only one that it breaks octet when it starts to lose the third electron, and that's our choice there. Okay, 15. Okay, this one is easy as well. Okay, shortest wavelengths means highest energy. And if you know our electromagnetic spectrum, okay, radio wave, microwave, both have low energy, IR have low energy, all 3 of them are actually lower than visible light. UV is a little higher than visible light, but not that much. No, doesn't do as much damage as X-ray, okay. And gamma ray obviously is the highest, but it's not here, so X-ray is our choice for the highest energy with the radiation that's shown in this question. And this next question, I believe in our actual exam, I was giving you chromium, not chromium plus, but chromium is one of those, number 24, this is one of those 2 exceptions that we talked about. Okay, chromium is argon 4s1 3d5 with a half filled orbital, 3d orbital. Okay, and with 4s1 and 3d5, your electron configuration in those last 2 or highest energy orbitals are like this. Okay, and count it, 6 unpaired electrons. Not much about the next question. Again, an easy calculation. Wavelengths equal to c speed of light over frequency. So 3.00 times 10 to the 8 meters second over 90.9 times 10 to 6 hertz is 1 over second. So 3.3 meters. All right. Five, 7, 4 plus 1, 34 electrons, 17 pairs. So that's your electron count. AS, fluorine, 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 fluorine. 16 pairs used, and 1 pair goes on the central atom. Now, so formal charge would be 5, the original valence electron count, minus 1/2 of bonding electron, 4 bonds, 4 single bonds, 8 bonding electron, minus 2 non-bonding electron, 1 lone pair. So that's -1, so that's your right answer, D. Now, electron affinity, that should be an easy question because your electron affinity increase now, across going bottom to top within the column, and increase from left to right in a row. Okay, so elements on the higher and upper corner is going to be having higher electron affinity, and that higher on the right is the area of the nonmetals, and you only have 1 nonmetal here, and that's your chlorine. Yeah. And I believe this question on the exam is the smallest, but that doesn't change the way that we approach this. Yeah. All 5 particles listed here, okay, has the same electron configuration. If you look at it, these guys are number 38, 34, 37, 35, and 36. Okay, so losing 2, you get 36 electron. Gaining 2, you get 36. Losing 1, you're getting 36. Gaining 1, you get 36, and this is already 36. So everybody has the krypton electron configuration. Okay, and now then that means they have the same number of core electron. Why do you mention core electron? Because we talked about how Zeph is important in determining ion size. Effective nuclear charge should equal to, okay, the actual nuclear charge minus number of core electron. And since all of them have the same electron configuration, so all of them have the same number of core electron. Okay, and that means whoever have the highest Z value would have the highest Zeph. So highest Z value is this. So this is the highest Zeph, and lowest is 34. So that's your lowest Zeph. Now you want the smallest size. Smallest size means least control from the nucleus over the valence electron. Well, least control means lowest effective nuclear charge, and obviously B is your choice here. And that's every question on the exam, and hopefully everybody can look into their mistakes on the exam and maybe going back to your notes, video lecture, or whatever, and correct them and get ready for the final exam.